3, 2, 1. We are live.
Hello, everybody, and welcome to another episode of the ContinualAI seminars. Today we are with Tyler Ace from Rochester Institute of Technology, and she will give a slightly different talk than the ones we are accustomed to. In fact, today's talk is titled Real-World Considerations and Applications for Continual Machine Learning. And if I understood correctly, it's basically a summary of her recently defended PhD thesis on continual learning, with maybe some extras here and there, right? And also, this may be the first time we host a discussion about PhD thesis, so I can't wait to hear it. Without further ado, I'm now leaving the stage to Tyler.
Great, thanks so much, Andrea. Good afternoon, everybody, or good evening, or good morning, I guess, based on where you are. As he mentioned, today the talk will be a little bit different. I'll be going over some of the work from my dissertation as well as my collective body of research as a whole. I think somebody is echoing a little bit.
This is strange. My microphone is shut down.
Okay, I think we're good now. Sorry. Okay, great. So yeah, I'll be going over my body of work. A lot of works were included in my dissertation, as well as some additional works that I think fit well into the continual machine learning picture. So without further ado, I'll present real-world considerations and applications for continual machine learning. So since many of us are in the Continual AI organization, we already know a lot of the benefits that continual learning can bring to AI in general. If we have agents that can learn and adapt in real time, we can make immediate inferences about new data to understand how well the agent is understanding its environment or new instances of objects that it's learning about. If we are doing things in real time, we could potentially deploy these applications on device. If we're deploying things on device, this could potentially reduce privacy concerns, since we don't have to process data externally on something like a server or in the cloud. Another benefit is transfer of knowledge. A lot of tasks in the visual world share a lot of similarities. So if I've learned something in the past that has a lot of visual similarities with something I'm learning now, the hope would be that the agent would be able to learn the new data more efficiently and perhaps even better than it would have been able to learn it from scratch, because it would be able to transfer some of those learned representations from the past. And in general, continual learning can result in more efficient learning algorithms. Some of the improvements that we've been making in the continual learning field could be beneficial for other fields as well that are adjacent to continual learning in general. Specifically, this opens the door for many new applications. Today, I'll be talking a lot about on-device learning, but there's several other things you could imagine that continual learning could be useful for, right? Things like robotic agents that maybe are traveling around and learning about a new environment or learning about new objects or instances within that environment. Things like user personalization for smartphones, right? I think we've all maybe been subject to things like Amazon personalization of ads over time. Other things that could have user personalization could be things like home appliances, right? Maybe I have a smart fridge that could learn my preferences over time for different types of foods. More recently, I think a lot of traction has been gaining in the AR, VR world, right? So augmented and virtual reality helmets. Specifically, we could use something like continual learning to update and localize object coordinates in a specific user's environment, right? And we could localize those and update the changes over time so that the user has a more personalized experience. Again, if we're implementing these things on device, we have a couple of considerations. Because these are hardware limited, we potentially have to consider the amount of memory that our algorithms are using. We also have to consider the amount of compute time that it takes in order to make inferences, right? If I have a smartphone and I want to be able to do something in real time, it's not going to be really feasible if I have to wait an hour or two in order to get an answer to the type of question that I'm posing or something like that. And again, the advantage of not having to send data externally to be processed is that not only could we reduce privacy concerns, but it could also be used for places where maybe we don't have internet, right? Like maybe I have an agent that's traveling around on Mars and I want to understand how well it's understanding its environment, but maybe it doesn't have an internet connection right now, right? If it's doing all of this processing on device, when it eventually receives an internet connection, then we could understand what it's actually learned over time. So I think that there's a lot of applications that could be benefited from the use of continual learning. Specifically, I'm going to outline my particular desired continual learning criteria. I think that maybe some other researchers might differ, but specifically in this talk, I'll be focusing on these. So I would desire a system that could learn and recall immediately from a single example. I call this online continual or online streaming learning. So on the right, I have an example of this, right? The agent would see a picture of a cat and then perhaps have to update and immediately be evaluated, and then maybe sees an instance of a dog and it's immediately updated, right? The learning and inference is happening in real time, one after another. The next thing is really important, and I think that maybe there hasn't been as much focus on this, but learning data in any order without catastrophic forgetting. I think in the computer vision field specifically, a lot of us are familiar with the training paradigm where we basically learn classes incrementally one at a time, right? So maybe you learn the dog class, and then the cat class, and then a bird class. And the problem with this is that the agent suffers from catastrophic forgetting of previous knowledge when updated on new data. But I also think it's important to test the other extreme, right? An IID, or independent and identically distributed data stream, is randomly shuffled. And this is typically what an offline neural network would be expected to see, right? This should induce the least amount of forgetting because the agent is revisiting previous classes. But I think that it's important that we test both of these capabilities as well as all of the data orderings that could come in between, because when we have an agent that's deployed in a natural environment, we don't necessarily have control over the acquisition of the data that it's receiving, right? It's going to be having maybe a video camera on board to collect frames, and it's just going to have to process those in the order that they come in. It might not necessarily have control of that. So let's make sure that it can work on any data ordering and not suffer from catastrophic forgetting. The next thing is heavily related to the on-device learning, but learning using limited memory and compute overhead, right? I mean, this is going to be application specific. Some people might think it's okay to have a little bit more memory for their particular application, but specifically a lot of my dissertation work focused on limiting the amount of memory and compute that we require. And the final thing is scaling to large-scale, high-dimensional problems. What I mean by this is, a large-scale problem could be a problem that consists of many classes, perhaps 1,000 or more classes, maybe thousands or millions of instances from those classes. High-resolution imagery. High-dimensional could consist of things like multimodal data streams, right? Perhaps at every time step, my agent isn't just receiving one input from the environment like an image. Maybe it's receiving both an image and an audio stream, right? Or an image and a question to go along with that image. So I think that these capabilities are highly desirable for a continual learning system, and specifically, that's what a lot of my research has focused on addressing. So just to make sure that we're all on the same page, I'm just going to spend a brief couple of slides going over how we set up the continual learning problem for vision specifically. So there's two major paradigms in which people have mostly studied this problem. The first is what I'm going to call incremental batch learning. This is the traditional computer vision paradigm where we break a data set into several batches. Typically, these batches consist of one or more classes. In the example on the right, we are learning the cat class, and then we learn the dog class, and etc. So at each time step, the learner receives a batch of data from one or more classes. It can then loop over that batch until it's learned, and then it's subsequently evaluated after learning the entire batch. I argue this has a couple of caveats. It's slow in a variety of ways. First, you have to wait for the data batch to accumulate before you can update the agent. You have to wait for the agent to loop through that data. And then there's perhaps a delayed evaluation, right? Because if my agent hasn't necessarily finished looping and batching over all of the data it's received, it doesn't necessarily make sense to evaluate how well it's performing. So this could delay how long until the human actually understands how well the agent is understanding its environment. And the other thing is that it's not necessarily reminiscent of how humans and animals learn. It's not like I go throughout my daily life receiving these large batches of image instances and then I'm processing them and looping over them, right? When we're active during the day, we're viewing a temporal stream of inputs and we're learning those one at a time as we're receiving them. So I argue that this is closer to what I'm calling online continual or online streaming learning. And this is motivated by how instances have natural temporal correlations, right? In our natural visual world, I'm receiving something like a video input over time. Or you could imagine, like that robotic application I gave earlier where the agent is traveling around its environment, perhaps with a video camera on board, collecting frames of data that it would immediately like to process. So specifically in this setup, at each time step, the learner receives a single new example from its environment. It learns the example and then it's evaluated. Similar to the incremental batch learning paradigm, there's no reason that we couldn't structure the input stream based on classes, right? So in this example, we can see that we're still learning the cat class and then the dog class, etc. It's just that my agent is receiving one input at a time, it immediately updates, and then I can immediately evaluate how well it's doing. The other constraint is that the learner is only allowed a single loop through the entire data set. So the advantages of this are, like I mentioned before, it's closer to how we as humans and animals process our visual stimuli. And I argue that it's better suited for real-time applications just because we can immediately process the frames and understand in real time how well the agent is doing. So the last piece to how we set up the incremental learning problem is that some folks perform a base initialization or pre-training phase before continual learning. You could imagine that, I use my favorite data set to pre-train some neural network, like a convolutional neural network, on a data set or a subset of a data set in order to have a pre-trained feature extractor, right? Universal feature extractors are commonly used in several applications like robotics. So I think that this is a reasonable assumption. So the way it works is we have an offline pre-training phase where you can train on the first N classes and examples, your first batch of data, an entirely separate data set and then you train the neural network on that data set, and then we perform a continual learning phase after that. So this is just a typical setup. And in 2020, we had a couple of questions about this base initialization, right? The first question is, if we do this, how good are the features? Are those features actually useful for continual learning? Is this an okay assumption to make? How well do they work? If the features are already good, do we even have to continue updating the features, or could we just train the output layer of the neural network or just the classifier, right? So to do this, we published this paper called Lifelong Machine Learning with Deep Streaming Linear Discriminant Analysis in the CL Vision workshop at CVPR in 2020. We won the Best Paper Award, which was kind of cool because I received a GPU, which helped me with the rest of my PhD. So for those who aren't familiar, deep streaming linear discriminant analysis has actually been widely used in the data mining community, right? We were not the first people to use this, and it's commonly used for learning from data presented in any order. A lot of people in data mining use it on IID data streams. So we were interested in using it as a baseline and testing how well it would work for these modern computer vision applications. So the strategy goes like this. Pre-train your favorite CNN backbone on either a subset of the data set or an external data set. Given a new image, we can push it through that feature extractor to obtain an image feature. And then we can perform an incremental LDA update, which basically maintains one running mean vector per class and a shared class covariance matrix. And then during test time, SLDA assumes that data is Gaussian distributed, and we can make Gaussians in feature space defined by those running class mean vectors and shared covariance matrix. And then we can compute the distance of a new image feature to each of those class specific Gaussians and assign it the label of the closest one. So we ran some experiments on the ImageNet 1K dataset, and I'm showing you the learning curve on the right of how well each of the methods performed every 100 classes trained in the ImageNet dataset. So at the time of publication, iCarl and end-to-end incremental learning were the state of the art. I know that this has changed since then, but basically what you can see is that SLDA has pretty strong performance. It actually outperforms iCarl at nearly every increment, and it actually ends higher than this end-to-end incremental learning baseline. So it has quite competitive performance, but I really argue that the strength of SLDA is not just its performance, but the fact that it only requires 30 minutes to train on 900 classes from the ImageNet dataset. This is over 900,000 images. It processed them on a Titan XP GPU and just a standard work machine in just 30 minutes. So this is quite impressive, as methods like iCarl took about 60 hours to train on that same hardware, right? So this is a significant speed up. In fact, it's over 100 times faster. And the other thing is that SLDA is a memory-free technique, right? It doesn't require any replay data. It doesn't really require much storage beyond just that the square covariance matrix. So it actually only requires about 0.001 gigabytes of storage beyond the CNN for this large ImageNet problem. So that was pretty awesome. Of course, SLDA comes with pros and cons, right? It works on different orderings. We tested in the paper several different orderings. It works in the IID scenario. It works in the class incremental learning scenario. It's incredibly fast, and it's a pretty strong baseline. So I argue that based on these 3 bullets, the algorithm is suitable for embedded device learning because of, its incredibly fast nature, and it's also very limited in terms of its memory and compute. The cons are that it only updates a shallow output layer, right? It's not doing any representation learning to actually make stronger features. So we'll talk about that in a little bit, but just keep that in the back of your mind that that is one of the limitations of SLDA. So continual learning for embedded devices is kind of an interesting direction, right? Embedded device is a device that is purposefully built for its application. You can think of something like your smartphone or a VR or an AR headset, right, that are specifically designed for the applications. They're typically resource constrained because of the hardware constraints. So we have to consider how much compute, storage, and power our algorithms are actually using when they're deployed on these types of devices. So we decided to study continual learning in mobile convolutional neural networks. So we found that SLDA worked really well, and we were interested to see how well other lightweight methods worked in this continual learning setting. So typically, a lot of people use the ResNet 18 backbone for continual learning, right? This is commonly used by methods like iCarl or BIC or Lucier. So this is kind of the gold standard that we've been using for a long time. But there's a lot of neural network choices, specifically in the convolutional neural network architecture. And there's a lot that are a lot smaller and require fewer resources than ResNets. Specifically, we were interested in how well the MobileNet v3 architecture and the EfficientNet architectures worked. So we chose both the small and large version of MobileNet v3 and then the 2 smallest EfficientNet architectures. So our incremental learning setup looked a bit like this. We would pre-train a mobile convolutional neural network using supervised learning on the ImageNet 1K dataset. And then just like SLDA, we would incrementally update the output layer of a CNN using supervised continual learning on a different dataset, right? So just like SLDA, we give an image, we push it through a pre-trained backbone to extract an image feature, and then we can continually update the output layer during continual learning to make predictions. So we had several objectives of our study. The first was just to perform a comprehensive study of how well mobile CNNs worked when they were paired with online continual learning methods. I think that recently more researchers have been looking at different architectures for continual learning, right? We saw a paper just a few weeks ago in the AI seminar here on transformers, right? But I think largely that a lot of researchers in computer vision have just been focused on using ResNet architectures. So first, we just kind of wanted to understand how well some existing algorithms worked when they were paired with different backbones. The other criteria here are kind of more interesting. So testing the ability of methods to generalize from very few object instances. This is really important in an embedded setting, right? If my agent can learn very quickly from very little data, this is desirable because it's going to learn much faster and potentially generalize better. So specifically, we were interested in what I'm calling out-of-domain generalization, and I'm kind of giving you an example of what I mean by this on the right. So with out-of-domain generalization, you could imagine that I train on these bicycles under different backgrounds or different illumination changes or different orientations. And then basically my classifier would be still expected during test time to perform well in an unseen domain, right? So what changed here was not necessarily the bicycle class itself, but the backdrop that it's on. So I'd like my agent to be able to generalize to these unseen domains. Specifically, I think that this is kind of interesting, right? Because if I had an agent in my home and I wanted it to understand specific objects that I wear, like maybe my pair of glasses, and I get a new couch or something, I would still like it to be able to identify those new or that same pair of glasses in this new environment or on this new other object, right? So I think that this setup kind of makes sense. The next bullet is to test the ability of methods to scale and perform well on imbalanced data, right? We want to be able to perform well on those large-scale, high-dimensional problems that I mentioned earlier. And the other thing is imbalanced data streams. The natural world around us is not balanced. Some classes are very highly prevalent, right? Like we see a lot of instances of people every day, maybe a lot of instances of cars, but maybe there's some classes that we don't see very often, right? Like tigers or something like that. So I would like my agent to be able to perform well on both very frequent categories as well as less frequent categories. And the final thing is to be able to evaluate methods across several performance axes. So a lot of times we just measure classification efficacy, right? How well is my algorithm performing in terms of classification accuracy over time? But also we need to consider things like memory used by the agent and the amount of compute time it takes to actually run the algorithm. So for this study, we studied several different methods. These were mostly chosen due to their ability to perform online continual learning, one example at a time, and also due to strong performance from previous research. So we studied a fine-tuning baseline that basically just updates the output layer of a neural network using stochastic gradient descent, no methods to mitigate forgetting, just kind of a lower bound on our performance. We implemented a multi-class online perceptron. So perceptron basically at each time step updates 2 weight vectors. It updates the weight vector for the correct class, and it also updates the weight vector for the highest predicted incorrect class. So it's always updating 2 weight vectors. We also implemented a streaming one verse rest classifier that basically compares new examples to a class mean vector, but it also considers that new example's distance to all other classes in feature space. Nearest class mean classifier, so basically just keep 1 running class mean vector per class. When you get a new sample, check which mean vector it's closest to and assign a label. This was used in iCarl. It's also been used in numerous methods since. Gaussian naive Bayes, so this is pretty similar to SLDA. It basically stores a running mean vector per class, and instead of a shared covariance matrix, it stores 1 running variance vector per class. So we were storing variance vectors instead of full covariance matrices to save space. But because you're only storing a variance vector, this does assume that the dimensions of that vector don't covary with each other. So it does assume that features are independent from one another. This is a pretty strong assumption. So Gaussian naive Bayes, sometimes isn't always the assumptions of it aren't always satisfied in practice, but we were still interested to see how well it performed. And then we tested SLDA and everybody's favorite replay method. So for replay, we tried 2 variants, one that stores 2 instances per class. The reason for doing 2 per class is basically that's sort of similar amount of memory as all of these other methods. And then also storing 20 instances per class, which is what is commonly done in a lot of literature. So in order to evaluate how well methods performed on those three axes, classification efficacy, memory, and compute, we adopted this net score metric, which was proposed in 2019. So omega is the net score metric, and this is the formulation for it on the right. So A of M on the top is basically measuring the final accuracy of a model, right? So this is considering that classification efficacy, how well does my algorithm actually work? And in the denominator, we can see that we computed the number of parameters used by the model and the compute time needed in minutes for the actual experiment. These alpha, beta, gamma parameters are basically just hyperparameters for, or just parameters that are tunable by the human to weight the emphasis of these different components on the actual score, right? Typically, we care a lot about classification efficacy. If my agent can't perform well in terms of its efficacy, it's not super useful, even if it is not using a lot of memory or compute, right? So typically people weight this alpha a lot higher than they weight beta or gamma just because they want to put more emphasis on performing well overall. So in order to evaluate methods, we studied several different data sets and orderings. So we used 3 different data sets. So the first is OpenLoris. Some of you might be familiar with this. So OpenLoris consists of videos that were captured from a robot of 40 different object classes, with each object class consisting of between 1 and 9 object instances. So in total, there are 121 unique object instances in this data set. The cool thing about OpenLoris is that each object instance was collected under 4 different domains, which I'm showing you on the right. So different clutter, different amounts of clutter, different illumination changes, different amounts of occlusion, and the pixel size of the actual object in the frame. And the other thing is that they were collected under varying difficulties. So I'm actually showing difficulty from easiest to hardest going from left to right, right? So you can see I have headphones, a mug, and glasses in all of these, right? And from left to right, they're getting more difficult in the domain pictured, right? So we can see that this pair of headphones doesn't really have any clutter, but as we move to the right, they're in a very cluttered setting, which is going to make the problem a lot more difficult. So for this data set, we studied two different data orderings. The first is what I call instance. So this basically means, for those 121 object instances collected under these 9 times 4 different domains and difficulties, I have over 4,000 unique object instance videos. And I basically take those videos in their temporal order and I just shuffle those around. So you're still learning the videos in the temporal order in which they were collected, but you're just learning, maybe I'm learning under one clutter scenario for an object and then a different occlusion scenario for a different object before a different clutter scenario for the first object, right? So this is kind of reminiscent of maybe what a human or a robotic agent would perceive in revisiting classes, but having to learn from those temporal correlations. The other data ordering is what I'm calling low shot instance. So in the instance ordering, we're using all of the videos of all of the object instances under all of these different domains and everything. But I argued earlier that it would be interesting if we could have an agent that learns from very few examples and it can generalize to out of domain inputs, right? So for this setup, we just used one randomly chosen object video from each of the 40 object classes, but then we still tested on the full test set. So this would basically mean that maybe my agent just sees this one pair of headphones under a very non-cluttered environment, but during test time, it would still be required to generalize perhaps to the pair of headphones under this different illumination condition, right? So it's testing how well the agent can understand those objects and generalize to unseen domains. So the other data set that we use is Places 365. Typically, I would use ImageNet for these experiments, but because I pre-trained my backbone on ImageNet, I didn't want to perform continual learning on it. So instead, I used the Places 365 data set. So this is a scene classification data set with 365 unique classes. It consists of places like the beach, restaurants, indoor environments, outdoor environments, things like this. And it has over 1.8 million images. So we use two versions of the data set. The first one, just consisting of those 1.8 million images, is used to understand how well the methods scale, right? So it's high resolution imagery, hundreds of classes, millions of images. But we also studied a long-tailed version of the data set. So a couple of years ago, some researchers proposed throwing some of the data from the Places data set away to make it long-tailed, right? Some classes have a lot of examples, some classes have very few, and the agent is still tested on the full balanced test set. So it's basically required to learn from an imbalanced data stream, but still emphasize the importance of each of the classes in that stream. For this one, we tested two different data orderings, just IID, where we randomly shuffle all of the video frames together, or sorry, just the static images together, and then class IID, where we learn one class at a time incrementally. So the first, I kind of structured the experimental results as a series of questions. So the first question is, how well do the methods generalize from very few instances? Because this instance ordering and low shot instance ordering of the OpenLoris dataset use the same test set, we can directly compare how learning from very few instances actually directly impacts the model performance, right? So the first thing that's kind of interesting to look at is the methods that had a huge gap between their instance and low shot instance performance, right? So we can see that this perceptron and fine tune method actually performed quite well when learning from all of the object instances. But when we threw a lot of the domains away and required it to generalize from just a few videos, you can see their performance suffered significantly, right? There was a huge drop in performance. Overall, we found that the methods on the right here, nearest class mean, replay, and SLDA, they performed quite well in both of these settings. But obviously, there's still a gap between learning from very few instances and learning from all of them. So, some future work needs to be done in addressing that gap. So the next question is, how well do these methods generalize over time? So I'm just showing you the learning curves of all of these methods when learning from the low shot instance data ordering, evaluated after every single object instance was learned across 3 different backbone architectures, right? So what's kind of interesting, I don't expect you to look at all of these learning curves, but what's kind of interesting is the strong performance differences between some of these methods, right? For example, naive Bayes in green. So with ResNet 18, you can see it performs quite poor. nearly, reaching chance performance by the end of the stream. But what's interesting is with the efficient net backbone, or this MobileNet v3 large, it's actually competing quite well with some of the top performing methods. Recall that naive Bayes makes this independent feature assumption, which basically indicates to me that the ResNet 18 features are not independent, right? These features that are extracted from that backbone aren't independent. And so maybe, some of these other backbones are actually providing us a little bit more rich feature representation. Overall, across architectures, we found replay and nearest class mean to perform the best. Right, so that's in gray and brown, and you can see that those are near the top for all of these curves. So the next question is, how well do these methods perform across a variety of axes? So I had mentioned earlier that we're interested in this net score, right, that takes into account classification, efficacy, memory requirements, and compute requirements. So on the left, I basically took the mean over all of the architectures, right? So this is just like fine-tuned performance across all of those backbone architectures tested. Yes, the metric can be negative, so that isn't deceiving you, that is true. So we can see that fine-tune performed quite poorly. This is mostly due to its poor classification efficacy, but we can see that nearest class mean and replay and SLDA strike a nice balance between those three metrics, right? And on the right here, I'm actually showing you performance across the 6 different backbones. As expected, ResNet 18 performance with the net score is the lowest for each nearest class mean, replay, and SLDA. This is to be expected since that's actually our largest network. So in terms of parameters, it has the most parameters. It requires the most compute time to push images through the backbone to extract features. So it's not surprising that in terms of the net score, which weighs memory and compute requirements, it performed quite poorly. As expected, some of these networks that don't require as much memory and compute had higher net score values. So next, we were interested in studying how does the actual backbone choice affect performance. We talked a little bit about it just now, but on the left, I'm basically showing you the performance of each of the backbones averaged across methods. So I took all of the continual learning methods, I averaged their performance across backbones, and then I'm plotting those results here. So what you can see is that the efficient net backbones provided the highest performance, and ResNet 18 was the poorest, right? So there's over a 20% performance gap, which is kind of interesting, just since we use ResNet 18 so commonly in our experiments. It makes me wonder if maybe we should be considering some other backbones. On the right, I'm just showing you the performance of ResNet 18 versus efficient net v1, which were the best and worst performing method or backbones. What's kind of interesting, right, is like methods like naive Bayes are severely impacted by this, and this is due to the assumption that features are independent from one another, right? And obviously ResNet 18 is violating this. But it is interesting that methods like SLDA are very robust, right? There's only a 3% performance drop when I actually change the backbone. So yes, it's performing better with efficient net, but it doesn't matter as much. So I argue maybe in the future we should consider using efficient nets because not only are they yielding better performance, but they also require fewer computational resources. And so the final experiments here are how robust are the methods to scale and imbalance. So these are the results on the places data set. Recall that we use both a full version and a long-tailed version, but they use the same test set. And I took the harmonic mean across orderings, right? So I tested both this IID shuffled ordering and a class IID catastrophic forgetting type scenario ordering, and I took the harmonic mean between them, and then I plotted the results here. And so what we can see overall is that most methods perform more poorly when the data was long-tailed, except fine-tune and perceptron, which just had very poor performance in general. But some methods were less affected by the long-tailed nature of the data set, right? Like nearest class mean only dropped by about 3%. When I switched to this long tail setting, whereas SLDA dropped by nearly 8%. So some methods are more robust to imbalance. So in summary, we studied the robustness of online continual learners across a variety of axes that I consider to be useful for embedded learning. Specifically, here's 6 different things we consider, right? So omega is that net score that considers classification efficacy, compute, and memory. The ability to learn from temporally correlated videos. Recall that this was the OpenLoris instance ordering, the low shot instance ordering of OpenLoris, right? This is the ability to generalize from very few inputs and to do out of domain recognition. the ability to scale to large-scale data, those were the Places 365 experiments, and then the ability to perform well on imbalanced data streams. So I basically took all of those experimental results that I just showed you, and I kind of came up with a way to normalize all of their performance scores onto a single 0 to 1 metric, and I made these radar charts on the right. So we can actually kind of see which methods performed well on which axes. In parentheses, I'm showing you just like the average score across those 5 different axes. So, you know, it's kind of interesting, right? Like Perceptron and Fine-Tune perform quite well when learning from video instances, but they're performing quite poorly across these other, you know, maybe imbalanced or scaling. And at the bottom, we can see that nearest class mean, replay, and SLDA, they have, you know, very good performance in terms of the net score, learning from videos, learning from low shot videos, and an ability to scale, right? So overall, the takeaways here are just, if you're going to do online continual learning for embedded devices, maybe you should start with these baselines. Maybe start with an SLDA, a replay, and a nearest class mean baseline, and build from there, right? I'd also argue we should be using efficient CNN backbones. But I mentioned earlier, what about representation learning, right? None of those methods were doing representation learning. They were only being used to update the output layer. And so to do this, we published a different paper, and it's motivated by the following. So humans and animals learn by storing compressed representations of temporally correlated experiences in their hippocampus. So for replay, you know, typically we just store raw inputs or raw feature vectors in a replay buffer. But this isn't necessarily consistent with biology. In fact, maybe we're storing compressed representations from higher in the visual processing hierarchy. When we go to sleep at night, these representations get consolidated to our neocortex, which is used for more generalized learning. So to address representation learning for online learning, we published this paper in ECCV 2020 called Remind Your Neural Network to Prevent Catastrophic Forgetting. This is all of my great collaborators who worked on this project with me. And so the Remind architecture is inspired by 2 theories in neuroscience. So the first is hippocampal indexing theory that basically states that when we're learning during the day, the hippocampus is storing indexed representations in its memory, right? And then when we go to sleep at night, using complementary learning systems theory, those indexed representations get reactivated and consolidated over to our neocortex to learn more generalized representations. And so the Remind architecture works kind of in the following way. We can first pre-train a neural network in an offline setting, right? Just like those other methods, and break it into two different networks. So the early layers are going to be called G and the later layers are called F. And then basically given a new input, we can push it through the early layers that we keep frozen to get a mid-level feature tensor, right? So this is just like your middle of the CNN tensor vector or tensor feature. We can then do the following. We can encode it to compress it to be a more efficient way to store it in memory. You can see in red here, I'm storing it in my memory buffer, and maybe I have some other inputs in my memory buffer in green here that I randomly select. I combine those all together. I push them through a decoder to reconstruct them back in the original feature space. And then I can use those reconstructed inputs in order to update the plastic layers of my neural network. So this does allow us to do some feature representation learning here in F, and we're doing it in a more memory efficient way because we've now compressed those representations. So here's some results on the ImageNet dataset. We compared methods that run in that incremental batch setting that I talked about earlier, as well as this streaming setting. So what's interesting, right, is I think a lot of us might be familiar with this BIC algorithm, right? It works very well when it's run in the batch setting. In fact, it's the highest performing method here. But when I run it in the streaming setting, it performs quite poorly, right? In fact, all of these batch methods perform quite poorly when I force them to learn, you know, from very few examples at a time, only a single pass through the data stream, et cetera. Whereas our Remind method makes a nice compromise between being able to operate in the batch scenario if you want it, but also performing well when learning in an online streaming way. On the right is the learning curve for all of these methods on ImageNet when trained in the streaming setting. And so basically what we can see is that Remind in orange is the top performer here, and the next top performer is SLDA. But what's kind of interesting is to directly compare SLDA to Remind, right? Remind does 2 things beyond SLDA. Not only does it store stuff in a memory replay buffer, it also updates feature representations, right? So it almost kind of directly shows us the impact of how storing some memory some data in a memory buffer or updating feature representations can gain us some performance benefits. The other thing that's nice is Remind is order agnostic. So again, earlier I argued that we should be testing different data ordering scenarios. We tested it on several different data orderings on the Core 50 dataset. So shuffling the data stream, that two class-based orderings, and then instances where I'm learning different video instances. You can see that Remind's performance is nearly unaffected when I run these different data ordering scenarios, whereas some other methods are a little bit less robust, right? Like fine-tuning has significantly worse performance in these class setups. The coolest thing about Remind, though, is that it's more of a general framework for doing incremental learning, right? It's not just an architecture or a component that's bespoke to just classification, right? It's just this idea of storing compressed representations from high in the visual processing hierarchy and then updating some plastic layers of a neural network. So this means that it's very easily extended to other problems. So we've actually used Remind for online continual learning for both visual question answering and object detection since we published it a couple years ago. So visual question answering, for those of you who aren't familiar, is basically this task where we give an agent a multimodal input at each time step. So it receives a natural image and a natural language question about the image, and then the agent is required to reason about that image in order to answer the question. This requires different things based on how the questions are asked, like maybe the agent has to understand how to count, maybe it has to do some attribute detection, scene classification, things like this, right? So at each time step, we give it the question and the image, and then we require it to learn from that in order to output the correct answer. To study how robust the methods are to different data orderings, we studied two. So the first is just randomly shuffling the data stream together, and the next is to actually make use of the visual question answering setup where we can actually organize the data stream by question type, right? So maybe I first require the agent to learn about counting questions, and then I require it to learn about attribute detection, and so on. So this is kind of an interesting setup that is unique to the visual question answering problem. So here are some results on the Clever dataset. If you're not familiar with Clever, it's a multi-step compositional reasoning dataset. So here's an example, right? Are there an equal number of large things in metal spheres? So first, my agent has to understand how many large things there are in the image, how many metal spheres there are, and then reason about if there's an equal number of both of those. On the right, I'm showing you the performance of 4 different methods, including Remind, in both that IID and question type data ordering when compared to an offline baseline. So basically higher performance is better. What's interesting is I thought the IID shuffled ordering would actually be the easiest, and it is for fine-tune extreme and SLDA. But what you can see is actually Remind's performance is significantly benefited from using this question type ordering. So it's kind of interesting to think about, you know, maybe some curriculum, maybe this question type ordering is forming some type of curriculum for Remind's performance that's making it perform much better in that setting. The other thing that I mentioned is that we use Remind for object detection. So we published this paper 2 years ago in BMVC called Rodeo, which stands for Replay for Online Object Detection. And on the right, I'm basically showing you the learning curves for that Rodeo method compared to an extended SLDA method and a fine-tuned baseline on the COCO dataset. So COCO consists of 80 object categories, and we required the agent to learn each of those classes one at a time. So you can see that, you know, Rodeo has the best performance, but SLDA with a streaming regression component isn't far behind. And this runs significantly faster and uses fewer resources. So if you're doing something like on-device learning, maybe you can just start with this simple SLDA plus streaming regression approach. And the final thing to consider is a lot of these are using that pre-trained feature extractor, right? SLDA used it, the mobile things used it, Remind uses it. So a natural question is, what about better pre-trained features? There's several ways we can do this, but within the last couple of years, I think we've seen a lot of improvement from self-supervised learning techniques, right? So in a paper last year at BMVC, we asked, how could self-supervised pre-training benefit continual learning? And so we studied this with Remind and several other methods. On the left, I'm basically showing you the performance of using 3 different self-supervised learning techniques to pre-train a feature extractor for the Remind method. So specifically, this plot is for Remind. And I'm showing you the performance improvement over using supervised pre-trained features, right? So you can see that overall, no matter the number of pre-trained classes that we used, all of these self-supervised features were performing much better than using just supervised pre-trained features. So this was kind of interesting, right? Not only do they provide better features, but it's also nice because it doesn't require labeled data, which can be expensive for human annotators. What's even more interesting is that it works so well even when I only use 10 classes for pre-training, right? Typically for ImageNet, we break the data set, the 1,000 classes up into these 10 batches of 100 classes, and we learn those 100 classes in these batches. But what happens if I only pre-train on 10 classes? You can see that the Suave pre-trained features actually perform quite well for Remind. In fact, here's the learning curves on ImageNet, and you can see that here's the old Remind in orange, right? And if I just swap out the pre-trained features for Suave instead of using supervised, I get a 14% relative performance improvement at the final time step just by using self-supervised pre-training. So this is kind of interesting, and it begs the question of, what type of pre-training makes sense for continual learning? So I've talked about a plethora of things today, a lot of things. But in general, online continual learning can facilitate several new applications. I think on-device learning is exciting, but I think there's a lot of other places it can be used. It makes immediate updates, immediate inferences, potentially fewer privacy concerns. And specifically, I discussed several criteria that I expect these systems to have. Let's learn one sample at a time, learning from any data ordering. Let's limit the amount of compute and memory overhead, and let's perform some tasks beyond image classification. There's a lot of future directions that we could go in. I mentioned just now better pre-trained features. We just used the state-of-the-art methods from the time, but I think self-supervised learning even in the last year has grown even more. So there's a lot of other methods. We could try larger or more diverse pre-training data sets, some techniques to improve the low-shot learning setup, techniques to improve robustness to additional domain shifts, right? Maybe we have, with a self-driving car, we have changing weather patterns, or maybe we have changing illumination conditions as it goes from day to night. There's a lot of other domain shifts. And I think open world learning can also be interesting, right? Not only to learn these new things incrementally, but also identify things as unknown and then incrementally update to understand them. So thank you. I know that was a lot. If my research is interesting to you, feel free to check out my website or email me with any further questions. And I think there's a little bit of time left for specific questions.
Thanks, Tyler. My head's hurting a bit, but it was a wild and very interesting ride. No, really, thanks for this amazing presentation. It gives me chills seeing how many options we have for continual learning. And I also think that was quite an effort on your side, right? So it's a summary of how many years of work, like 4 years or something?
6, but we can pretend it's 4.
6 years. So, in 50 minutes, I think it's a good result. So, first thing first, since I know everyone's wondering, which GPU did you receive from NVIDIA?
The Titan RTX.
Oh, nice.
Yeah, I mean, there's certainly better ones now, but I'll take anything that's free, right?
Exactly. And then, for embedded devices is something that, you don't need a V100, right, for embedded devices.
Very true.
But on a more serious note, before opening the floor to the attendants here, feel free, of course, to open your mic if you want to ask a question to Tyler, or to type the question in the chat, to use YouTube. Just let us know if you have any questions in any way. But maybe I can start with well, it's not really a question actually, but from your talk, it seemed to me that many problems that we are now addressing in continual learning with neural networks and adaptive computations and stuff can really be solved, or at least effectively tackled with simpler techniques, provided that you have a good feature extractor, right? So if you have a very good feature extractor and you are able to address with that extractor different tasks, then you can just do classification with some statistical methods, so non-adaptive ones, let's say. And so you basically remove the problem of forgetting, at least in the output layer, but you don't have the problem of forgetting in the hidden layers because they're fixed. So do you think that for most of the problems, we should actually switch to this kind of approach because that simply works best, and there's no problem in this kind of approach? How much do you think this can face and tackle real world applications? So do you think that in some particular case, maybe, or in many cases, maybe you need to update your model, so you cannot rely on a fixed feature extractor? So in general, do you think that the results you just showed to us are widely applicable? And that's something, because it all worked really well. I mean, it's impressive. Or instead, for different cases, we are going to need to work on continual learning, even with neural networks that are continuously updated.
Yeah, I mean, I think this is a really important point, right? I think when I started out doing research, there were a lot of methods that weren't studying just using a pre-trained fixed feature extractor for continual learning, right? But I think it simplifies the problem, and that's good and bad, right? It's good because it can get us really quickly a bunch of baselines to see what is possible if I don't necessarily update features, right? If I just have some pre-trained feature extractor, what can I expect my performance to be? And I think that this is a good place to start, right? If we haven't worked on a problem before, for example, object detection, when we worked on that project, I think it was really just a straightforward thing to think about, okay, well, what can we just extract features from and then apply on top to solve the problem at its most basic level. So I think it's a good approach for getting started, but I definitely think that some problem domains do benefit from updating the feature extractor itself, right? For example, I mean, we saw that Remind's performance over SLDA was quite significant. So I mean, SLDA has quite competitive performance, but I do think its performance was improved further by actually updating the feature representations. But it does come with its own set of problems, right? It requires more time if you're actually training the feature extractor, right? We actually have to update a bunch more parameters. We also have to potentially deal with catastrophic forgetting in the backbone itself now. Potentially we have concept drift if the features change too much over time. But I do think that it still has some benefits. Right. I think, especially depending on your problem domain, if the representations of what your domain looks like from the starting point to the ending point are changing drastically, then I think it's important to actually update those features to be accommodating to the newer data that you're getting in. So, I mean, I think both approaches have merit. If you're getting started, I think a first approach should just be, what happens if I pull an off-the-shelf pre-trained backbone and I apply the simplest, statistical method or something else on top just to train the classifier, right? That's my absolute baseline. And now what can I do to improve that even further? So I think that's kind of the approach that we've been looking at, but certainly I still think there's value to updating the feature representations.
Yeah, I kind of agree. I mean, when looking at forgetting, of course, the performance is really strong, but then we may want to look at other metrics like forward transfer, the well-known ones in continual learning, which we all want to study, but actually rarely study. But yes, in this way, I mean, the forgetting is not that much of a problem, but of course, freezing stuff prevents to forward knowledge from future tasks, and there are other problems connected to it. But at least we have a way to address the forgetting problem. And I was also pretty impressed by the self-supervision advances, right? So just with more robust features, let's say, you gain quite an amount of final accuracy. So that was also really interesting to me. Well, I have a few other questions in the order of thousands, but maybe we can leave others to ask some questions. Does anyone have any questions for Tyler on her work?
I just have just curious about like what make you want to dive into like continual learning?
Yeah, I mean, I think the first paper that got me excited was EWC. So my formal training in my bachelor's and master's was in mathematics. So the first paper that I grabbed back when I was starting out was EWC, and I got very excited about all of the mathematical implications that had. As you can see, I didn't really do much with regularization-based methods throughout my dissertation, but I still think regularizing parameter updates could be a feasible strategy for dealing with forgetting if you pair it with something like replay or some other mechanisms. So I think that was probably the first thing that got me pretty excited. I also think it makes sense for these more generalized applications, right? We as humans continually are adapting and evolving over our lifetimes. I don't think it makes a lot of sense to train a system in a static environment and then just expect it to perform well on future data that it's never seen before. So I think just the application setting of continual learning itself was interesting enough for me to want to pursue it further. I also think there's a lot of directions to go with it, right? I mean, I talked about a bunch of different things that you could do here, but I think that it's not just closed-ended. I think there's so many different things you could tackle, right? You could tackle just the classifier or the feature updates or a different problem domain or adding some other complexity, maybe like open world learning. There's so many different areas that you could tackle that it seems appealing in that sense.
Yeah, I got another question that since we already can continue learn like image classification or object detection and so on, is it possible to do we continue learn image classification task, and then we continue learned in object detection task, then we test them together like that?
Yeah, I think this is kind of interesting, right? And I'm not sure if a lot of researchers have looked at this, but I think it makes a lot of sense that maybe I want my system to be able to perform a bunch of different types of tasks, right?
Yeah.
And potentially those could feed into one another, right? I mean, object detection takes image classification just a step further, right? We still have to classify things, but we also have to localize them. So, I mean, I think it could make a lot of sense to consider, different applications in the same setting. And I think that makes the most sense for eventually developing autonomous agents that could learn how to do several different types of things. But I think it's a bit understudied right now, and maybe because it's more difficult than maybe it's because it's difficult, maybe it's just because a lot of people haven't been looking at it. But I still think that could be an interesting direction. Yeah.
Yeah. Thank you.
Thank you.
Unless we discover that there's one pretrained models which can do everything in one shot. But yeah, any other questions for Tyler? Okay, maybe I have just one last question about Remind. So I was very impressed by the curriculum result you achieved on with Remind. And I'll take no as an answer, but do you have any idea why this is happening with Remind? Do you think that it's something due to the data set, or can be replicated with different kinds of data set? Is a property of the strategy of Remind itself? Because I haven't seen many curriculum learning results in continual learning, but it seems pretty natural to have some.
Yeah, I mean, I think this is very interesting. I will say when we got this result, we reran it a couple times because we thought it was a bug. We actually thought that we ran something incorrectly and, wanted to verify that everything was correct. So I do find it a bit surprising, right? I mean, like I was saying, I was expecting the IID data ordering to just be the best for all of the methods. What's kind of interesting, I mean, the unique thing about Remind compared to these three other methods, right, is that it actually updates the feature representations. So maybe something in conjunction with the way that the task stream is ordered has, benefit from actually updating the feature representations. I will say we didn't study it much further than this, but I do think it's still interesting. And I think to study these data orderings, it probably makes sense on a problem like VQA, right, where you have this nice reasoning backbed or test bed to kind of understand what's going on, and perhaps you can poke and prod at the models to try to understand why they're performing better. It could also maybe be an easier place to set up task difficulty, right? So maybe like what is an easy question versus what is a harder question to try to learn that. Yeah, so to answer your question, we didn't dig at this further, but I do think it's interesting, and I think it could be something to explore in future work.
Yeah, it was very surprising to me. So it's, well, we'll see in the future. I may, by the way, I've missed raised hand before by Jonathan. I don't know if he has a question for Tyler. Maybe not. Let's give him some more time to unmute in case. Well, no problem, my mistake. Oh, there's something in the chat. Okay, he's typing the question. And congratulating for the defense. Yes, this was basically a PhD thesis defense. You're having lots of external supervisors and reviewers here. Apparently, you're passing the defense. So the main question is arriving. In the meantime, before asking the very last question to Tyler, I'll just take one moment to remind all of you of the possibility to become a ContinualAI official member now for the current year. Or if you already are an official member, you can renew your membership to be valid in this year. And apart from supporting ContinualAI, which is good by itself, you will get some benefits like the right to vote in the upcoming elections, or you'll be offered discounts in events that we are planning to have in the near future. I mean, there are some perks associated with it, but you can find all the details in the ContinualAI website. Just look for the Join Us page on the left menu. You'll be all set. And yes, I think in the meantime we have the question. So Jonathan asks, do you think that taking this cognitive science justified approach to the design of Remind is something the continual learning community could embrace more?
Yeah, I mean, I think there's pros and cons, right? I mean, we as humans do continual learning and we're quite good at it, right? I mean, we learn a lot of different things over our lifetimes. Catastrophic forgetting, I guess, maybe it happens and maybe it's okay, right? Maybe we forget some things that don't necessarily need to be remembered and it's not detrimental to carrying on our daily tasks. So certainly I think that there is some inspiration that we could take from cognitive science or neuroscience to try to understand better how humans do this in order to inspire us how to do it in AI systems. Certainly, I don't think we have some pre-trained supervised feature extractor from ImageNet and then just learning a classifier on top, right? We probably are updating some feature representation. So in that sense, maybe it does make sense to consider that. But yeah, I mean, I think that there is some room. There's a lot of other things that we could consider. You know, none of my algorithms are models of the brain by any means. They take very loose inspiration. So I think that, you know, there's a lot of other work that could be done in integrating different components from, cognitive or neuroscience to do that. What do you think is the reason the findings of the continual learning to move further into RL or IL? So I assume reinforcement learning. Yeah, I mean, I think reinforcement learning, I'm not an expert in this domain, hasn't yet moved into RL. Oh, okay. Yeah, I mean, so I guess first, I think reinforcement learning could be really interesting, right? Because it has an actual feedback loop from the environment. I think, you know, we as continual learners are using feedback from our environment in order to improve our world models. So I think that that could be interesting. I certainly am by no means an expert in this field. So yeah, but I think that that could be something interesting to consider in the future. Why haven't we yet moved into RL? I mean, I think that there is some literature on the continual RL domain. I think I'm a little bit less familiar with it, but I know that there are some researchers out there who have been working on it. But yeah, I mean, I certainly think it's a lot easier and quicker to get results maybe on things like image classification or object detection, right? They don't require thousands or millions of episodes to train. It's a nice test bed. You can quickly get results. You know, even ImageNet, I say quickly, maybe it takes, you know, tens of hundreds of hours to run, but maybe that's still faster than some of the reinforcement learning algorithms. So I think, you know, maybe some of the progress has just been due to the complexity of the problem. People want to solve it maybe in this more simplistic or easier to run experiments domain. But I certainly think that there's still merit with reinforcement learning. I definitely think that this environment input could be really useful and beneficial for improving the actual algorithms themselves, right? So I guess those are kind of my thoughts from a high level perspective as someone who doesn't study reinforcement learning directly.
Yet.
Yet.
Who knows, right?
Yeah.
Okay. So it seems your answer was satisfactory. Okay, great. Any last minute questions? I don't think so. So, okay, I would like to thank Tyler again for taking the time to be here with us all this time. Thank you very much. And I invite you all to be here again for the next ContinualAI seminars happening on Thursday, as usual. We will try to understand what this new X model scenario is all about and how it's related to continual learning. So thank you for staying with us, really, and I'll see you on Thursday. Bye, everyone.